I didn't know that Takeshi sent the mail to you. I discussed with him today, and so he said that you still can submit your homework today. So I will not interfere anymore. So you will just, as he told you, then give it to him. So yesterday I just counted, there were 7, which means that's 2, right? Okay, so please then give it to him. Today we will continue to discuss quarks. And last lecture we considered classification of hadrons. And what has been established that the hadrons form families with 8 components and also 10 components. And this can be mapped onto properties of SU3 group, because SU3 group has representations 8 and representation 10, and one can do classification according to this SU3 group, and amazingly properties of the particles in these multiplets fit quite well the properties of the components of 10-plet and octet of SU3 group. One of the questions which was left is why there is no particles in fundamental representation of SU3. This is the question. SU3 has fundamental representation 3, and where are particles, and do they exist? Which transform with this, which transform under this representation 3. The second question, this is the first. The second question, the families which we have observed are in, say, representation 8, which belongs to higher order representation of SU3, and the 8 in particular can be made out of product of 3 times 3 representation. So what is the physical meaning of this product? What is the physical meaning? That particles are transformed as a product of fundamental representations. Unique answer to these questions has been done by Mireille Gell-Mann, George Zweig, and Yuval Neumann. By the way, Zweig started as particle physicist, but then he moved to neurobiology, so it's interesting. That, I was wondering, I checked what this kind of record, what the guy did after this, because we know what Gell-Mann did and Neumann did, and I just realized that it stopped to publish in high energy physics, and then I realized he moved to neurobiology. It's interesting as well. So what is the answer? And the answer is that hadrons are composite states of more fundamental objects. Quarks, they call quarks, which transform under fundamental representation of SU3. So Q is transformed under 3 and anti-quarks transformed under 3 bar. So we use the following notations for the quark triplet. And again, let me remind what is the meaning when we are saying that these particles form the triplet, which is transformed under triplet representation of SU3. This means that eventually we construct some theory of interactions, Lagrangian or Miltonian, which is functional of the operators of these fields, or wave functions. And this Lagrangian is invariant under, in this case, SU3 transformation of these fields, which means that you do transformations, and then Hamiltonian doesn't change the form. So we always skip this story, but when we are saying so the particles are transformed under representation 3, in this case, we mean all this kind of formalism that eventually we think about some Lagrangian, which actually depends on these fields, which is formed by these fields, and so we do transformations, and Lagrangian is invariant. Okay. So, in particular, according to Gell-Mann, Zweig, and Neumann, mesons are composite states made of quark and anti-quark. This means that the wave function of meson is transformed as the wave function of quark and wave function of anti-quark. And each of them are transformed as representation 3. And this is the origin of this product of 3 times 3. Okay? So since meson is the product of 2 wave functions and each of them, or operators, transform under representation 3 and 3 bar, then the product is transformed under this 3 times 3 representation. Okay? So, we explain what happens with this fundamental representation of FP3, and we clarified what is the meaning. They actually connected, and so this reflects that mesons are composite states. Their operators are, or their fields are the product of the fields of quarks, and therefore the product is transformed as the product of representations. Now, baryons in this picture are composed of 3 quarks. Q, Q, and Q. Therefore, the wave function of field of baryon is made of the product of 3 fields. Each of them is transformed under representation 3, and therefore baryons are somehow should transform under some representations which are made of the product of 3 times 3 times 3. And remember, that contains 10, it contains 8, it contains another 8, it contains singlet. And so, for instance, 10-plet, which we have discussed, is in this representation. And the octet of baryons with proton and neutron is here. So baryon number is additive quantum number, and therefore to have for proton baryon number 1, we can ascribe for each of the quarks baryon number 1/3. So let me put the baryon number of quark is 1/3, and anti-quark minus 1/3, and then the baryon number of baryons is integer. Later, even more complicated systems of quarks have been found. You might be heard, this maybe not. Pentaquarks, which are made of 5 quarks. An anti-quark, so it's quark, 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 like this. So this is pentaquark. So these are very unstable situation particles, and always kind of confusion what you have really some new hadron, or it is just system of baryon and methan, right? So I will not discuss this. Maybe some of you will work on this. Now, question: what is connection of quarks with Trieste? Who knows? Yeah, yeah.
The James Joyce wife.
Yeah.
Yeah.
Yeah, James Joyce was living here, and Gell-Mann took this name quarks from novel of James Joyce, who is saying 3 quarks for master mark. Actually, I tried to translate, never managed to translate the meaning of this sentence from this poem. Anyway, maybe some of you know how to translate this. I tried to translate this to Russian, to Italian, didn't manage to pick up the sense. Anyway, so the quark is in the statement of James Joyce, and James Joyce spent a lot of time here in Trieste. I don't know if he has written this poem being in Trieste or where, but someone can explore and investigate what is this. Now, questions about quarks.
So, does fundamental representation mean that we have a fundamental particle in terms of we cannot reduce it more?
I have no answer to these questions. For time being, we haven't seen the structure of quarks. Well, it is not excluded that you have also some substructure of this. It may happen, right? For instance, we have discussed isospin. And isospin has fundamental representation 2, right? Proton and neutron transform as fundamental representation of SU2. But now we know that proton and neutron are composite states.
Yes, because
this is one example.
That fundamental representation was embedded in the octet, which is not a fundamental
Yeah, but the same story may repeat again. So that's I don't know. So you can actually make even triplet out of. So for instance, 3 times 3 contains 6 plus 3. Remember, and therefore I can say, okay, so my quarks are made of again, that's a product of 2 objects. For instance, one is fermion, another is boson, and they transform as a triplets, and they form this representation 3, in spite of the fact that. Okay.
Yeah, but for example, for electrons, you know that they are leptons, and they, for example, under quantum electrodynamics, they obey the Spinorian representation of that theory,
Yeah.
which is not the fundamental representation. But
So
this does would this say anything about a substructure about electrons? Does this algebraic concept?
So again, even there were some models of composite quarks and leptons. It's not only what you are guessing. So the answer to your question, no, I don't think that, that the fact that the particle transforms under fundamental representation means that the particle should be fundamental and has no structure.
And another question about mesons. Mesons have particle and the antiparticle at the same place. Is that possible? Like can we confine, for example, electron and positron into
What do you mean in the same place? Well, still these particles have some finite size. I cannot say that the wave functions are in the size of the pi, for instance.
Isn't there an annihilation possible for the quark and antiquark?
Well, if they have the same properties, in principle, yes. Yeah. So and we will see actually the weak decays of pi is in a sense annihilation of quarks inside the pi. Now, let us discuss properties of quarks. Some more questions? Well, simple, right? So we have these octets, and then we realize that they are transformed as not a fundamental, but these more higher representations. And we are giving interpretation of this fact. And so in this way, we are coming to the idea of more fundamental objects. See, people got Nobel Prize for this. I'm teaching kids, so maybe some of you will get eventually Nobel Prize. You see, everything is simple. Huh? If you just move in the right direction, it's also important, you know. So, some people think that one should really do very complicated things and you are successful. So, in many of these cases, things are really very simple. It's just on the surface, right? You just need to have a correct move. So properties of quarks. They can be established from known properties of hadrons. So quarks should have spin 1/2. Then you can reproduce integer spin for mesons and semi-integer spin for baryons. Of course, you can try some more complicated, such spin 3/2 or something like this. But this is simplest. Just simplest. And it works. Then eventually it was even checked. Now, baryon number is 1/3 for quarks. So other characteristics can be reconstructed knowing characteristics of hadrons. So we can get from here characteristics of quarks. And for this, we can use the quantum numbers which we have introduced so far. They are additive quantum number, and therefore the electric charge of hadron is given by the sum of electric charges of quarks which compose a given hadron. So the same is for baryons. I will not write this. The same is for strangeness, and strangeness of hadron is given since it's additive quantum number, and we check this using different processes in terms of hadrons. It's the sum of strangeness of quarks. So I put here I. Let me put here I. And here is. And the same is for third projection of isospin. The third projection of isospin of hadron is given by the sum of the third projections of quarks, which compose a given hadron. So in the case of mesons, we have two quarks, and therefore the sum is just sum of two terms. Yeah?
In principle, we only need two quantum numbers, isospin and hypercharge, and then all of them are determined.
Yeah, so there is a connection, and So electric charge, as we saw before, is a combination of isospin, S, and baryon number. It's like a formula, Nishijima Kubo. Now you will have an exercise, and I will prepare it already, so that you will use known properties of pines and K mesons, and you can reconstruct what should be the properties of three quarks. But one can do this systematically using group properties. Now, since we have this identification of our quarks and hadrons and the elements of SU3 group, we can do this just automatically to establish what are charges of quarks. So remember that in our identification or mapping, what we were saying, that operators of physical quantities are identified with diagonal generators of the group. We check this for the case of isospin, and in that case we have SU2. It has one diagonal generator, which is sigma 3, and it has -1/2 and -1/2 diagonal elements, which can be identified with eigenvalues of corresponding particles. Now, SU2 actually is embedded in SU3, and not only this, we used isospin also to classify particles within the multiplets of SU3. So SU3 contains SU2, and in fact in SU3 we have two diagonal generators, and one of them should be identified with isospin, because isospin is embedded in this SU3 group, and we have generator which is 1 square root of 2 with normalization of this type. This is lambda 3, and it has elements 1/2, -1/2, 0. It's diagonal, so I do not put here, these are zeros, right? And that can be identified with the third projection of isospin. So that 1 square root of 2 lambda 3 is the third projection of isospin. So now we have three components in fundamental, and therefore our identification is the following. So we have U, D, and S. So these are three quarks notations. And according to such a form of generator, we should say that isospin, the third projection of isospin of U quark is 1/2. The third projection of D quark is -1/2, and the third projection of S quark is 0. So which means that these two particles form isodoplet, so isospin doublet. They are transformed as doublet under SU2, and this is the singlet of isospin, so it has 0 isospin. It is singlet of SU2. Now there is the second generator, diagonal in SU3, with appropriate normalization to square root of 3 lambda 8. And it has the form 1/3, 1/3, and -2/3. I can write this generator in the following form. 1 over 3, 1 over 3, 1 over 3, plus 0, 0, minus 1. And I can identify the first one with physical quantity, which is baryon number. Right? And I can identify the second one with strangeness, with the operator of strangeness. So that our operator 2 over 3 lambda 8 is given by baryon number plus strangeness. And remember, we introduce notion of hypercharge. So that's hypercharge. So this operator can be identified with hypercharge. So then according to this prescription, strangeness of U quark should be 0. Strangeness of D quark should be 0. And strangeness of S quark is minus 1. Which is actually matches very well with what we learned, because U and D quarks with these properties, they form our usual particles, non-strange particles. They form proton, neutron, pions. Particles with strangeness, they should include a strange quark, because that's carrier of strangeness.
This is how they got names.
How? Sorry?
This is how quarks got their names, right? These properties.
Yeah, S is obviously this like this sort of strange quark. And U in D and is up and down, if you want. Up quark and down quark. So again, so here we are doing mapping, right? So again, what I was saying, there's some physics formalism, there's mathematical formalism, group theory, with some elements, and there are some physical quantities which we have introduced even before talking about group theory. So we introduced isospin before even. We introduced strangeness, right? So we introduced baryon number. Well, now we do mapping onto this SU3 group theory. So let me write again. We have U, D, S, and this is up quark, down quark, and this is strange quark. So these form isodoublet, and this is isosinglet. And let me write the table which summarizes the properties. U, D, S. Here is I3. This is 1/2 minus 1/2, 0. Strangeness, 0, 0, minus 1. Baryon number, 1/3, 1/3, and 1/3. And now we can find what are electric charges of quarks. And for this we can use Nishijima-Kubo formula, because so everything it matches well. So electric charge, according to this formula, is I3 plus B plus S over 2. And so I will not do this arithmetics, but you can check that, that this charge is 2/3. This is minus 1/3, and this is minus 1/3. So, and this can be established using these characteristics and such a formula, which acts at the level of hadrons. We check this, but it must also act at the level of quarks, because all these quantities additive quantum numbers, and therefore the same should actually work at the level of quarks. Again, you will have the problem. You can just, so we did this using group theory formalism, but you can recover all these quantities just knowing what is, say, pi 0, pi plus, pi minus, what is k 0, and so you can recover these quantum numbers. By the way, people of course tried other possibilities, and in particular, people didn't like this kind of not integer electric charges for quarks, and there were theories with integer electric charges of quarks. They existed for a while, but then it was proven that it doesn't work. So they used also played with color, because we will discuss color, and playing with the color, you can cook and first somehow very close classification also with integer electric charges, but then it was proven that it is wrong. Actually, we have even now direct measurements of charges of quarks. Questions?
Q is also a matrix, right?
What?
Q charge is also a matrix.
Yeah. So with these elements, right, so that will be 2/3, minus 1/3, and minus 1/3. So all these are matrices, and you can check that.
But this Q is an electric charge.
Yeah.
It actually is attached to the electrodynamical theory.
Yes, simultaneously, yeah. Yeah.
But it's at the same time one of the generators in the group.
Yes. Well, it is a combination, right? So there is also isospin. But you see what we are claiming, actually. We are claiming that these are the same parameters which appear in electrodynamics. What we are claiming here that strong interactions are invariant under change of electric charge, for instance. So clearly it should be connection, because we are saying that strong interactions are invariant with respect to substitution of proton to neutron, which is related to change of charge of the particle. And what we are saying, you can say this in this way, that strong interactions are invariant under change of electric charge. The same is with isospin.
And in principle, when we see the Lagrangian that involves an interaction involving quarks, you do not see the electric charge in that term, right?
So, we do not see charge in the part of Lagrangian responsible for strong interactions. But we see this in the part which is responsible for electromagnetic interactions.
Then changing, making a charge, making another charge configuration would violate the symmetry in the electromagnetic term?
Yes, but not in strong interactions. Again, so what we were saying that these strong interactions have a big symmetry. And this symmetry is not respected, so for instance, by electromagnetic interactions. So, yes, this is important to understand. For instance, strong interactions have this isospin symmetry, which we have discussed. And electroweak interactions, of course, no, because so proton has coupling with photon and neutron not in the lowest order. Right? Yes? So again, all this formalism, eventually, from the point of view of strong interactions, is to eventually claim that Lagrangian of strong interactions is invariant under all these transformations. Okay? So, now what we will do, we will move from hadron level to quark level, and we kind of make reinterpretation of what we learned before now doing this in terms of quarks. So now let us go back to weak interactions and to see how different processes, which we have studied before, look like at the quark level, our quark lepton level. So weak interactions. At quark level. So let me start with beta decay. Which looks like neutron go to proton plus electron and plus antineutrino, electron antineutrino. From the quark point of view, a neutron is a combination of U, D, and D quarks. So this is neutron. Now you can check that electric charge is zero, that you can check the properties, right? So U, D, and D. And so this is 2/3, minus 1/3, and minus 1/3. So they have now 3 quarks. In final state, we want to have proton, and proton is U, D, and U. Actually, you can check that it matches also isospin. So we characterize proton and neutron by electric charge and isospin. And so you can see that this matches these properties. Okay? So this is proton. And now to make this transition, we need to transform one of the D quarks into U quark. And therefore, beta decay at quark level looks in such a way that one of the D quarks transforms to U quark and emits pair. And you need, of course, sum up when this emission of pair occurs from this D quark. And such a decay, 2 other quarks play the role of spectators. They're just seeing how one of the quarks suffer and then decays, to make this transformation. So they call it really spectators. So 2 quarks are spectators, one has such a transition. And we have studied already this transition as described by the current. I think next year, if I will give the lectures, I will introduce this one parity violation before. So my idea was to have part of the course devoted to symmetries, and therefore I'm discussing parity and parity violation in the last part of the course. But I think it doesn't produce much inconvenience for you. I'm just writing this structure, but then will explain how that was established. So that is as far as this pair is concerned. But now we need to describe somehow this transition of D quark and U quark. Remember, at hadron level, we had transition of neutron to proton, and that was described by the current. Of this form. Right? So we have written this current before. Now, at quark level, we need to introduce current which transforms D quark to U quark, and that can be written as U, gamma mu. And let me write in general G vector coupling at quark level minus G axial vector coupling at quark, gamma phi, and this D quark. So, in principle, these parameters are coupling constant, right? So, so you have here also G Fermi. But it's also part of the coupling constant, right? So because, for instance, GA is coupling constant of axial vector current. A priori, it is not clear if the couplings at quark level should be the same as at hadron level. And so this is why I have written here GA, GV, and GA, which in general differ from 1 and this GA at hadron level. Because quarks are not free. I didn't mention this, but of course one can immediately ask how quarks are kept inside the hadrons. We haven't discussed yet this. So, first of all, it was kind of some period when people thought maybe just quarks, again, some phantom, they are not really existing objects, so this is something which is useful for classification. So it was really a long period before it was established that quarks are kind of real objects sitting in hadrons, interacting. And in principle, it should be very strong interaction between quarks to keep them inside the nucleons. Inside the nucleons, yes, inside the hadrons. And these forces can actually change the coupling constants in principle, right? So what we call renormalize coupling constant. We started with some coupling constants at quark level. We need to take into account that quarks have some other interactions, which actually kept the quarks inside the hadrons. And these interactions can change couplings. And so at hadron level, we have something else. Now, so let me tell you about this relation. So what I will discuss now, relation, and here we have 1 and GA. Here we have G quark V, G quark A. So what are relations between them? One important law, I will not go into details because it was whole the current algebra developed in the beginning of 60s which dealt with this problem. Well, I will be quite short, but just you will just hear these terms, and if someone will be working in this field, then it will be important to study in more details. So one of the important things, or principles if you want, is what we call CVC, which is conservation of vector current. So actually the same question you can ask also about electromagnetic interactions. We have these electric charges of quarks, 2/3, 1/3, minus 1/3, minus 1/3. Okay, so then we can introduce electromagnetic current with corresponding couplings. And one can ask the same question. Is it correct that at hadron level you should just sum electric charges of quarks at this quark level? Are they renormalized or not? And the answer is no, and this is because of this conservation of vector current, which actually leads to conservation of charges. And the idea is the following, that strong interactions do not modify vector currents. And this is because they conserve electric charges, and they conserve correspondingly this vector charge. Okay? So, like in the electromagnetic interactions, and this is the same statement. In electromagnetic interactions, we are saying that strong interactions do not modify electric charges. They do not renormalize. So if you introduce charges 2/3 at quark level and 1/3, minus 1/3 at quark level for d quarks, then the electric charge of proton is just the sum of this 2/3, 2/3, and minus 1/3 with no changes. So let me write electromagnetic interactions. Proton is U, U, and D composition. Now the electric charges of these are 2/3, 2/3, and minus 1/3, which actually give 1. And now the question is the same. Why strong interactions do not change these charges so that eventually for proton you would have something else? And they do not change the charges because strong interactions conserve, or this we are assuming, right, and we are checking this. So they are kind of state that strong interactions conserve electric charge. And actually we saw this in all these processes with nuclei, with proton, neutron, with hadrons. There is a conservation of electric charge, so which means the strong interactions conserve electric charge. So what does it mean? It doesn't mean that you may have strong interactions, very complicated, emission of some other particles, but at each time, in each of these interactions, electric charge is conserved. And that leads to the conservation of electric charge for whole the system. So, for instance, proton, we have these quarks with charges 2/3, 2/3, and 1/3, right? So we have this 2/3, 1/3, and 2/3, and minus 1/3. So this is U, U, D. We will study later. I will just give you kind of an advance some announcement, and you will understand this later. Strong interactions are due to interactions of quarks with gluons, which are analogy of, say, photons. And so what you will have in general, that strong interactions lead to the following processes. It can be emission of gluon, and then it's absorbed. Or it can be emission of gluon, which then transforms into quark-antiquark pair. It can be even some more complicated stuff. But in all these vertices, in all these interactions, electric charge is conserved. And therefore, if you have electric charge 1, say at these positions, you sum up what you have here and you will get 1. So if you take in another moment, and so that is time, it's going in this way. So you can imagine that your proton, or quarks inside the proton, in the course of propagation, they emit virtual gluons. The gluons are kind of producing virtual quark-antiquark, then they eventually annihilate. So, and you can check that if you take another moment of time, like here, gluon has 0 electric charge. The sum of electric charges in this system again is 1, right? You can look in another moment of time, so let me put here and a Q bar. So if you take in this moment of time, what you will get, you will have 5 now charged particles. However, since gluon is neutral, these quarks have opposite charge. And again, the total charge of whole the system, including this pair, is again the same, 1. So whatever complicated interactions, and you might have here also emission another gluon and some absorption, the total electric charge is the same as in initial state, and it doesn't change by strong interactions. So this gives you some kind of physics idea why strong interactions conserving electric charge do not lead to renormalization. And again, the charge of proton, even when you take into account interaction, is still 1. Well, that can be done in more kind of strict way, and but this is idea how it works. Okay? Now, here we deal with weak interactions. And here we deal with this vector current. So this is vector current. And then it was, again, principle that vector current responsible for electromagnetic interactions and vector currents responsible for weak interactions, they are of the same origin. They form triplet of currents. Because this is charge current, right? And in the case of electromagnetic interactions, we have neutral currents. And so they have all the same properties. And in the same way as electric charge and electric current is conserved, also vector current of weak interactions is also conserved. And therefore, this picture can be repeated for this weak interaction vector current. And therefore, G at quark level, V should be 1. So the charge at quark level should be equal to charge at hadron level. Like we saw here, the charge of the system at quark level, electric charge, equals electric charge at hadron level. In the same way, and this is what is conservation of the vector current hypothesis. That was hypothesis. And then it was checked by many observations. Explain why we have this equality. You know, this is very important because that actually one of very important steps is led us to the standard model eventually. Now, how about axial vector current? So we have this axial vector current, and here we have partial conservation of vector current. So it turns out that strong interactions respect vector current. They do not change corresponding coupling constant, but they do change the axial vector coupling. So you cannot repeat the same argument for axial vector current. Conservation is true, holds only for vector current, not for axial vector current. So here we deal with what we are saying, renormalization of the corresponding coupling. Let me say this. Strong interactions renormalize axial vector coupling. So that this GA at the quark level is not equal to GA at hadron level. So here strong interactions change the story. However, this change is not big. And here what is worked is PCA, C, which is partial conservation. Of axial vector current. So this hypothesis actually referred to currents, but from conservation of current, you get conservation of electric charge. I made this explanation in terms of conservation of charge. Here is partial conservation of charge. So what happens with this axial vector current is that the coupling is different, but not much different. And what has been found that actually the coupling at quark level, GA, is 1. And then at hadron level, it's 1.23. So this is effect of renormalization of axial vector coupling by strong interactions. Well, actually, this is for nucleon. This is for neutron and proton. In the nuclei, this coupling is again changed. Again, because you have that modification depends on the type of the hadron and the type of hadronic system. So that is an important issue these days because for nuclei, which people are using to search for neutrinoless double beta decay, this coupling becomes even smaller than 1. So this is for proton and neutron. This is for beta decay. This is for free beta decay. Yeah.
Having couplings bigger than one does imply a strong interaction between particles.
The strong interactions between quarks and gluons, that's what modifies this coupling.
But at the end we have a weak interaction process.
Yeah.
The end coupling.
So imagine that you have, say, let me, again, that's a bit advanced stuff. You have D quark and you have U quark, and you have here W boson. So that actually a real interaction which behind the current. But then you need to take into account the processes of gluon emission of this type. And then they change this coupling. So that's literally how it is.
If you go to the quark level, this kind of picture is true. But the whole process is somehow should also be solvable by perturbative methods.
Well, so unfortunately, you are at lower energies when perturbation theory doesn't work if you do beta decay. Yes, so that's picture for high energies when you can really use perturbation theory. So when you go, this is at quark level, you just have elementary vertex of quark interacting with W boson. But when you go to a real physical system, then you need to take into account this type of the corrections. And not only this, so these gluons also interact with other quarks, you can absorb by other quarks in the head. And so this is messy. I mean, conservation of vector current really simplifies everything. Whatever complicated interactions you have, you are saying, I have conservation of vector current and therefore conservation of the corresponding coupling. That's easy, right? Otherwise it would be. So, and we're still struggling, so that's measurement. It's not like we computed this. Although there is this famous theorem, which is Goldberger-Treiman theorem, Treiman relation, which actually connects this GA with, remember this coupling of pi and decay we introduced. They have kind of the same type of the source, and the coupling of pi with nucleons. So there's the theorem which made this connection. But so these couplings are now, they can be computed in principle, right? And people are using lattice to make computations for all these couplings. But not from kind of, I have no analytical solution, of course, for this. Actually, this violation of axial vector coupling is related, again, let me just give the name, and because you will hear this once you enter this field. This is related to violation of chiral symmetry. So what is this? So we have SU3, we have discussed SU3 group, right? Each fermion, or Dirac fermion, has left and right components. Have you studied this somewhere? So left and right. So you can introduce, so left quark, which is 1 minus gamma 5 over 2 quark, and right, which is 1 plus gamma 5 over 2 quark, right? So if you sum up, you will have a quark. What was noticed that actually strong interactions invariant not only when you do this rotation of quark wave functions, but even when you do separately rotation of left components and right components. So actually a real group is SU3 left multiplied by SU3 right. And this is what is called chiral symmetry. So actually the symmetry of Lagrangian of strong interactions is even richer, not just SU3. But Lagrangian is invariant when you do independent rotation or transformations of left components of quarks and right components of quarks. Actually, we saw this already in the case of electromagnetic interactions, which are invariant for left-handed and right-handed electrons, fermions. Yeah.
This left and right is in the same sense electrical, not electrical, but spin. Like quarks have spin in the same sense that electrons have spin. So
Yeah.
we can.
Now we discussed SU3, right? Till now, this SU3 flavor, if you want. When you do rotations in the space U, D, and S quarks, okay? So which means that we can apply these transformations 3 by 3 complex matrix, which will, mix these S quarks, so S, U, and D quarks, and Lagrangian is invariant under these transformations. Okay, so that's what I mean. Now it turns out that the symmetry is even richer, and in the first approximation, you can make independent rotations of left components and right components. So you can write your Lagrangian not in just in terms of U, D, and S quarks, but in terms of independent left and right components of these quarks.
These left and right components are in a representation of electromagnetical theory, right?
No, so again, so now I'm considering U, D, S left, and U, D, S right. So now I'm considering even 3.
So they are still in the same internal space?
Yeah, sure, yes.
Is it like quarks, the wave function of quarks transforms as spinors under Poincare transformation?
Yes, but I'm speaking here. About flavor transformations in the internal group, right? But of course, I have kind of confusion also with external symmetry because left and right are defined. But again, so I can just separate. So what's the problem? I can separate and make transformations independently. So the only what actually breaks the symmetry are mass terms, because in the case of mass terms, mass term can be written as Q left, Q right. I don't know if you studied this. So mass terms actually connect left and right components of fermions, and therefore they break chiral symmetry. So anyway, that's advanced stuff. Someone wants to study this, fine. I'm telling this that somehow this renormalization is connected to the breaking of this chiral symmetry. Dot. I don't want to go further at this point. But again, what is the most important for us here is this. This is what I will heavily use. So it happens that the situation at quark level becomes even simpler than at hadron level. At hadron level, we have this GA, which is different from 1. And the current was 1 minus, so gamma mu 1 minus this GA gamma 5. With this, we have the structure of the current, hadron current, which exactly coincides with the structure of leptonic currents. In the case of leptonic currents, it was gamma mu multiplied by 1 minus gamma 5. And now with this, we have completely the same for quark. This is extremely important conclusion, because it is in this way we can construct the standard model universal theory. Otherwise, you would have something different. If this at quark level axial vector current would be something different, then we would not have this SU2 cross U1 standard model theory. We probably should go for some maybe SU2 left cross SU2 right or something like this, some more complicated structure. So the most important conclusion from this discussion is that we can write Hamiltonian of weak interactions as G beta, I'm writing for beta decay, square root of 2. Then let me write this current as current with d quark. And here is leptonic current. And this d current, alpha here is Lorentz index. I'm using a set of mu because I will have mu also. Right? So this current now is U gamma alpha 1 minus gamma 5 d after establishing this. And leptonic current is given by neutrino gamma alpha 1 minus gamma 5 and lepton. And here is L, and L equals, okay, so let me put it here, this result. It's for beta decay, it's electron and electron neutrino. So the key point that both currents here have V minus A structure. So now let me discuss quickly decays other than beta decay. We have pi decay. And pi decay at quark level looks in the following form. So we have, let's take pi minus. And pi minus is a combination of two quarks, U bar and D. Agree? So you can check that quantum numbers matches this. And then decay of pi proceeds in the following way. These two guys annihilate, this is what you wanted, right? And produce pair of muon and muon neutrino. So that's diagrammatically shown here. And so what we see, the important conclusion, that to have pi decay, we need to have annihilation of d quark and u anti-quark. Right? So the d quark should be transformed into u quark. And this is the same transformation as it acts in beta decay. In the case of beta decay, we had also transformation of d quark and u quark. And we see at quark level clearly that the currents are the same. Remember, we had kind of general discussion before when we just assumed. So suppose this is the same hadronic current as in the case of beta decay and pi decay. But here at quark level, we see explicitly that both decays, beta and pi decay, are due to transition of d quark into u quark. So it's the same current when d go to u is responsible for both beta and pi decay. So now we can write the Hamiltonian as g, let me still write immediately gf square root, because they are very close. 2, and I write here g d quark alpha, and I'm writing here two currents. One is electron current plus muon current. So this is Lagrangian, which describes simultaneously beta decay and pi decays. And for muon decay, we had the product of these two currents, remember? So muonic current and electron current. That was for beta decay. Now let us consider strange particles decay. Yeah?
In the case of beta decay, the time direction with the transformation, it's go from down quark to u quark, but with the direction of time.
Yes, yeah. But it doesn't matter, it's the same current, because remember we discussed this algebra of reactions. You can always, if you have, you can always put, say, one of the particle on the left-hand side of the reaction by changing particle to antiparticle. Like in the case of, remember we discussed beta decay, but we also discussed scattering of neutrinos on neutron. And this is the same story. Now it's an algebra of reactions in terms of quarks. Because you are saying in the case of beta decay, you have D go to U, is what you want to say. And in this case, you have D, which annihilates with U. So what? This is algebra of reaction. You can always put.
But the problem is also if we change, for example, in the algebra of reaction, U with result with one component of the product, we got like free quarks in both sides.
I missed what you are saying. So here we still have some interaction. So in this point there is interaction. I have no free quarks in the sense that these transitions, both in this case and this, are due to some interaction, weak interactions. But you can do, of course, even such a story. You can do like this. This is U, and then you may have this process. When you produce U quark and D antiquark, you can turn this in this way if you want. And you can find the processes of this type, for instance. Actually, that can be obtained if you have, say, electron neutrino annihilation with positron excessive charge. So they have such a process. Okay, so let's go to decay of strange particles. We started already decay of K plus, for instance, into mu and mu plus. K minus into mu minus and mu antineutrino. At quark level, K plus has the structure U quark and S antiquark. Okay? Again, you will have this exercise, you will check how using K multiplets with K mesons and with pions, you can extract the properties of quarks and quark composition. Right? So that has strangeness +1, because S quark has strangeness -1, therefore this is +1. And electric charge matches. So you have here 2/3, and this is again +1/3, right? Because this is antiparticle. So what happens here when you deal with such a decay? These two particles annihilate and then produce mu and mu plus. So this is the process, and this decay is due to transition of then U quark to S quark. So that's transition of U quark to S quark. What happens here is you have this annihilation, but again using algebra of direction, it's the same current as when you have transition of U quark to S quark. Now, I mentioned already other decays of K meson, and K meson can have a decay like, for instance, K plus go to pi 0, again mu and mu. At quark level, this decay looks as follows. We have U quark and we have S antiquark. And this S antiquark can be transformed to U antiquark. So it's U, and here you might have such a process with emission of pair of muon and muon neutrino. So let me put here mu plus, and this is mu plus, and this is mu T. Agree? Because U bar and U, this is pi 0. And this is K plus. So dynamics is the following. One of the quarks is spectator and another one has such a transition. That's similar to beta decay, right? But what is important here, we also deal with transition of U quark to S quark. So this is in terms of anti-quark, but it's the same transition. So the same current which operates here is responsible for two-body decay of K meson. And so that is current which we call strange current. And it is given by U gamma alpha 1 minus gamma 5. And this strange quark. Remember we introduced strange currents in terms of hadrons. And now we see that all these strange currents which we introduced before actually are due to this transition at quark level. I put here again universal unit. Of course that was also checked. So you have again B minus A structure, even for this current. Decay of K mesons and other strange particles then can be described by G K for fermionic coupling. Then I put here strange current multiplied by electron current plus muon current plus Hermitian conjugate. Actually, I can add here also the current which we have introduced with D quarks. I can add here current G, D, and alpha. So remember I introduced such a current when I described pi decay or beta decay. And then the product of these two describe for me, for instance, weak decay of K plus into pi plus and pi 0 without leptonic pair. Now what is this GK? We have already discussed this. And GK is G Fermi multiplied by sine theta Kabiba. This is the way we introduced Kabiba. So now what we can do, we can introduce a mixture of currents or mixing of currents at quark level. Remember we introduced mixing of currents at the hadron level, and then looked like we introduced current H, which is cosine theta Kabiba, and then this is not strange usual current plus sine theta Kabiba S alpha. Before we introduce currents in terms of hadrons, and now this is at quark level. Okay, this is current with D quark, this is current with S quark, and this sine and cosine take care about difference of this fermion, four fermion couplings. So now my Lagrangian becomes more and more universal. So I can put all these terms actually in more and more compact form, and the Hamiltonian can be written as GF square root of 2, and then the product of complete hadron current multiplied by complete leptonic current, L alpha, and this leptonic current is the sum of electronic and muonic currents plus Hermitian conjugate. So you see I have more and more terms, but I put them, everything in more and more compact form. But let me focus a little bit on this. I can rewrite this as, so let me still change here immediately. Let me put here Q, because these are already in terms of Q, and then this is Q. Sorry. So these currents are in terms of D quark and U quark. This is S quark and U quark. And so let me put here Q. So instead of hadronic currents, now I have quark currents. And then this is the Hamiltonian. I can write this quark current again in more compact way. So it's interesting. I'm just rewriting things in more and more compact way, but I will eventually come with very important conclusion. I can write this as gamma alpha 1 minus gamma 5. And here what I will write is cosine theta Kabiba D quark plus sine theta Kabiba S quark. Plus Hermitian conjugate. So now I can say that here I deal with mixing of quarks. So that the combination, and let me introduce notations, du, and this is the combination which enters the same charge current with U quark, is given by cosine theta Kabiba D plus sine theta Kabiba S. So we came to a fundamental statement that there is a mixing of quarks. You see how it appeared? We had this kind of studies of decays of K mesons and non-strange particles, and we observed that a strength of decays with strange particles is somehow lower than G Fermi. Then we have introduced this mixing angle. Then we have written everything in more compact form, first in terms of hadron currents, and now we have written this in terms of quark current, and eventually we are coming to this mixing of quarks. So that this current can be written as alpha Q U gamma mu 1 minus gamma 5, and here I'm writing du. Sometimes people are writing this d theta, but then when I will introduce third generation, then it will be okay. I can use both notations. For time being, I can write either du or d theta. So I came to conclusion that quarks are mixed in charge currents. What are the properties of D and S quarks? They have the same charges, they have the same, well, they have different isospin properties, but they have also different masses. And so what I see here, that charge weak interaction currents mix quarks, so that U quark interacts not with just D quark, but with combination of D quark and S quark. Simple, right? But we will see that the things will be more and more fundamental later. So everything comes from these simple observations, and just the way of rewriting of different expression of the same expression. So now we can talk about doublet U and d theta, and this doublet expresses the existence of the current. So if I write it in this way, this means that there is a charge current which transforms U quark to d theta, or vice versa, d theta to U quark. Actually, this is the doublet which eventually appears in the standard model, weak interactions. Maybe I will stop at this point because eventually I will combine everything and will write Hamiltonian, which looks like extremely universal and simple. I will do this next lecture. Yeah.
Did we assume this, or we concluded from the mixing of neutrino property as we?
No, we haven't discussed yet mixing of neutrinos. So I just mentioned, but it was independent. So that comes from just measurements. Remember, we measured decay rate of K meson. We compared this decay rate with decay rate of pi. And so comparing these two decay rates, we can measure this. So this was measured. And then it occurs that we can just parameterize this coupling in this way, just use the same G Fermi, but then we need to multiply this by some parameter, which we call this sine theta Kadiba, which is smaller, of course, than 1. So it's 0.23 or 22. This is experimental fact. So this is experimental fact. And we have no theory for these mixing angles, as I said. So we measured this, this is something like 0.22 of the experiment. Like here, we don't still know why the quarks are mixed in this way, so why this combination appears. So now here we introduced mixing of quarks. And I hope you know what is the origin of this. So, experimental observation at hadron level, mixing of quarks, so mixing of hadrons, of hadronic currents. Then we go to quark level, and we deal with mixing of quarks at quark level, and final step, instead of mixing of currents, we can rewrite this as the mixing of quarks. Okay? So this is the next exercise, right? And, it doesn't matter, sorry, but it was something with some defect in printer.